Hi everyone. Um, I'm going to wait maybe 1 or 2 minutes just to let everyone join the call. So again, we'll start in 1 or 2 minutes. Hi everyone. Thank you for being with me today. My name is Christian Approximate, and I'll be presenting today's topic where I go over Nastran Solution 200 and how it can be used to perform optimization of, say, aerospace examples. So here's my goal. What I really want to communicate in this presentation is what the procedure is like for Solution 200. Um, which BDF file do you work with? How do you convert this BDF file to Solution 200? What entries do you need to perform optimization? Um, I'll then go ahead and discuss how do we know if our optimization went through properly. I'll go over how to view your results in Excel. And then at the end, I'll go over how to update the original model and update it with new optimized properties. This is part 4 or part 3 out of a 4-part series. Each week, I do a different presentation on Nastran Solution 200. For example, 2 weeks ago, I did an fundamentals of Nastran Solution 200, where I go over basically the basics of structural optimization. The following week and this week is where I go into actual structural examples with Nastran Solution 200. In these presentations, I go through every step you need to take to optimize your structure. And then next week we have, or actually that's tomorrow, we have our final presentation, how to perform sensitivity analysis with Nastran Solution 200. All of these are hosted on YouTube Live. So if you want the latest schedule, if you are interested in attending, you can come to my YouTube channel. Alternatively, you can send me an email here and I'll definitely get back to you with a link to the latest schedule. Just in case you need more though, if you need more than training, you want access to the Nastran Solution 200 web app, if you want guidance on an optimization project of your own, feel free to send me an email and I would definitely get back to you with a response. So here's what I have for today. We went over the goal. Again, the goal for today is to show you the procedure. What steps do you need to take to perform optimization with Nastran Solution 200? Before I go ahead and show you the procedure, I have to go over what size optimization is. There are a lot of optimization types out there, so I have to define this one, which we are going to specifically focus on for the presentation. I'll then have some comments regarding when to use optimization. I know many of you are in the aerospace industry, so you might be asking, when can I use size optimization? I'll go over the supported analysis types. It's very likely you are performing a solution 101, 103, or 105, or any other solution type with Nastran. You might want to know which solution types are applicable for optimization. And then I have 2 examples where these are relevant to the aerospace industry, and I'll show you what the step-by-step process is to perform these optimization examples with Nastran. So with that, let's go ahead and discuss our first topic. What is size optimization? So here on the slide, I have a built-up structure here in yellow. By itself, it doesn't look too significant. Here, if we isolate the elements, as you see here on the top right-hand side, you see this is actually composed of two-dimensional and one-dimensional elements. The 2D elements might represent the skin, as an example. The 1D elements could represent a stiffener, as an example. It's after assigning parameters to the elements that we finally have the fully defined structure, if you will. Here on this slide, there is a thickness parameter used to specify the thickness of the skin. Here we have dimensions of the beam cross-section associated with the one-dimensional elements. For size optimization, it is these parameters that can be set as varying design variables. The optimizer will literally modify these parameters to find an optimum, and that is what size optimization is. This is a big contrast to the other optimization types and topology optimization, as an example. This is sort of what a sculptor would do. He would decide what material gets to stay and what material gets to go. This is different from shape optimization, where you allow the boundaries or the profile of the model to vary. Here you can see the inward or inner faces are allowed to vary and produce this new optimized shape. Here we have topology optimization, where each element has a design variable of its own. And then topography optimization, where you have surfaces that are allowed to sort of, I suppose, warp. Warp isn't really the best answer. I'll say it's a process of allowing the nodes to move normal to one another. So again, in this presentation, we are focusing on size optimization. Sometimes you'll hear this referred to as parameter optimization. So now, when do you use optimization? There are a number of applications you can apply optimization for. One big item is weight. If there's a structure you have and you want to remove some material while preserving performance, you can optimize for weight. If there is a model, let's suppose you have a composite laminate and your current layup does not meet the failure criteria. It's actually violating some of the failure criteria. Optimization can be used to find a design that fulfills all of your so-called design constraints. Another example would be model matching. If you have a finite element model and then you have an experimental physical model, your FE model will produce a set of results. Your experiment will create a set of its own results. And then you find out that the simulation does not match experiment. With model matching, or rather with optimization, you can vary parameters of your model that will bring the FE results to better match experiment. That's something else you can do with optimization. And then performance. You might be dealing with the aircraft vehicle, and there are certain limits to performance that you want to maintain. If you were to optimize for weight, this would have an impact on performance. So what you can also do is study how minimizing the weight would impact the performance. That's something else you can do with optimization in Nastran Solution 200. On this slide, I have all the solution types that are supported by Nastran Solution 200. If you're dealing with a static analysis, buckling, dynamic analysis type, or even aeroelasticity, these are all analysis types that are supported by Nastran Solution 200. The list is actually longer. I purposely left out some solution types just because we are an aerospace audience, so I think these are the most relevant to you, the aerospace audience. Here on the right, I also have one comment. Just recently, MSC Software released a version of MSC Nastran that includes the capability of performing vibration fatigue. The benefit of this, beyond that it's now directly embedded in Nastran, is that you can optimize for fatigue. So I figure I should definitely put that on the slide just so it's on your radar. And now let's go over the first optimization example. This is a very introductory example to optimization with Nastran. I'll I'll take time to go over this setup. Basically, we have 3 rod elements at these nodes 1, 2, and 3. They're all pinned at the top nodes, and they're all connected here at node 4. We have 2 subcases. In one subcase or load case, we have a load applied in this direction, and then for the second load case, we have this other load applied in sort of a symmetrical direction. Now, what are we optimizing? So here's our optimization problem statement. Before you perform an optimization of your own, it's very important you have these 3 things defined. What's your objective? What are your design variables? And what are your design constraints? Here, our objective is to minimize the weight of the structure. Our design variables will be the areas of each rod element. We have one requirement though. The area of element 3 should match the area of element 1. And now for constraints, we want to make sure that the stress and tension is no more than 20,000 psi, and then the stress and compression is no less than negative 15,000 psi. And then we have a displacement constraint saying at node 4, this node is not allowed to move between 0.2 inches. Let's see here. So again, we are going to let the areas of the rod members vary. We want to minimize the weight while making sure that the stress and displacement constraints are within the limits. Full details of this exercise are in the Nastran Design Sensitivity and Optimization User's Guide, Chapter 8, and that should be 3-bar truss. So let me make that correction. So here is what I have to present in this upcoming tutorial, if you will. I'm going to use the web app to convert my Solution 101 PDF file to Solution 200. I'm going to create our design variables, objective, and constraints. I'm going to perform the optimization in Nastran Solution 200. I'm going to use Excel to view the optimization results. I'm going to view the results in Patran. And then at the very end, I'm going to show you how to update the properties in your original PDF file. So before we go ahead and get started, let me actually load the example. So here, let me go ahead and find this example. What I want to show you now is the current state of the model. What's the displacement and what are the stresses inside of the truss? What we are going to do is take that example and then optimize it for weight and the stress and displacement constraints. So here, let's go ahead and look at what we have here. So this is our baseline example. We'll go ahead and look at the deformations first, just to see what our current state is. And here I see that I have a displacement at node 4 of approximately 0.002 inches, which is good because that means I can make the structure less stiff, but still possibly be within the limit. So let me go ahead and show you what load case 2 looks like. And here, since the loading is symmetric, we have the same displacement but in the opposite direction. So here we have 0.02. I believe, let me look back here. Right. So we may potentially have to make these members a little stiffer actually to minimize the displacement. And now what about the stress? Let's go ahead and look at the stress. So I'll go and select load case 1. And then I'll show you what the X component will look like. So here is what we have in terms of the axial stress and the elements. You can see that we currently have an axial stress of in compression of 9,000 psi here, 4,000 psi and 1,000 psi here, and this is all in tension, and then this is in compression. And we see the same thing for load case 2. It's just it's symmetric, so you have the values in opposite sides. So again, we want to make sure we avoid tensile stress, or a stress in tension of 20,000 psi, and we want to make sure that the compressive stress is above negative 15,000 psi. So now let's go through the process of optimizing this model. One thing we'll be using is the Nastran Solution 200 web app. Again, this will let me convert my Solution 100 BDF file and convert it to Solution 200 BDF file. It will let me create my design variables. It will let me create my objective and my constraints. The really special thing about this web app, it will create the entries automatically for me. Here, as this little demo shows, as I type and interact with the web app will immediately create the necessary entries for me and update them as I make modifications. Traditionally, you might have to type these up by hand. You might have to pour over documentation to understand how everything's connected. Alternatively, you might have a pre-post processor where you have to click dozens of times in a program that already has dozens, hundreds of buttons to do this. But the web app, its sole purpose is to generate your Solution 200 BDF files. Here's another example. As soon as I select design variables, you see that my necessary entries are automatically created for me. If I want to modify the boundaries for the design variables, I can easily use the web app. And as you see here in the output is automatically updated for me with little need to click 100 times in an application. So let's go ahead and get started with the process. And for this, I'll start off with this BDF or DAT file. This BDF file has an entire description of the 3-bar truss, as a description of the node points, the elements, the loading, and all that stuff. I'm first going to copy all of this, and then I'm going to load the Nastran Solution 200 web app. So let's go ahead and do that right now. If you're interested in getting access to this web app, please feel free to email me, and I'll definitely be glad to work with you on getting you access to that. So to start off with, let's go ahead and paste the BDF file here and click on Identify Design Parameters. The web app will identify everything that can be set as a design variable. Here, it's identified cross-sectional areas, Young's modulus, a Poisson ratio, and a density. I can select these 3 areas as design variables, and in the next table, you see the design variables have been created for me. I can then establish my bounds. So for this first design variable and every other one, we want to make sure that the lower bound is 0.01 inch and the upper bound is 100. And here, keep in mind, the design variables are automatically updated for me with 0.01 and 100. And then we have to link to these design variables for me. I want to say that the value of design variable 3 or x3 is going to drive the design variable 1 value. So x3 drives x1. Here I have a D-link created for me that specifies the association between those 2 design variables. So this completes the design variables. Let's go ahead and create our objective. Here's a long list of all the response types I can set as objectives. Here, I'm interested in setting the weight as a design objective. Of course, I want to minimize it. And now let's create our constraints. Here, we have to create 2 constraints. One constraint. One for stress, and then one for displacement. For the stress, let's configure the stress. We'll say we want to apply the stress to P rod elements, and we want to specifically select the axial stress. I can alternatively set the torsional stress as the limit, but here I want to set the axial stress as the limit. And this is applied to properties 11, 12, and 13, and the bounds, negative 15,000 psi and 20,000 psi. And for my displacement, I want to constrain the x and y displacements. X corresponds to the T1 component and y corresponds to the T2 component. If I look here, there is a T1 and T2 here, and let me zoom in just so you get a better look. I can select T1 and T2 here, and now I can select the grid point, which is grid 4, And for my bounds, that would be negative 0.2 and positive 0.2. So negative 0.2 and positive 0.2. And then here on the right, as always, I have my statements automatically created for me. Let's move on to creating a constraint group. Yes, you've created your constraints, but now you have to select which load cases these constraints apply to. I'll go ahead and click on Add All Constraints to Group. This basically creates one constraint group with all the constraints, and I'll apply this to all the subcases or load cases. And like before, the necessary entries created for me. Let's go ahead and move on to the exporter. I've created my design variables, my objective, and my constraints. The web app has built all the statements I need for the variables, the objective, and the constraints. The other thing it's done, it's converted my original BDF file to Solution 200. Here on the right is the original BDF file. It's Solution 101. But now it's Solution 200 on the left. It's optimizing for statics. There's a pointer for the objective and a pointer for the constraint group. So perfect. Let me go ahead and download local copies of this to my desktop. So I will go ahead and click download BDF here and here. And on my desktop, on my downloads directory, is this optimized BDF file. So now what I can do is start Nastran and perform the optimization. So let's go ahead and do that and click run. Again, if you have any questions, comments, feel free to leave me a comment or question in the chat box. Alternatively, you can send me an email at christian@theengineeringlab.com and I'll definitely get back to you. So let me go ahead and run the optimization. And in a moment, we'll go ahead and explore how to view these results in Excel. And after the optimization is finished, the first file you should look at is the F06 file. At the very bottom, you'll find a message here that says run terminated due to hard convergence. This is indication that a successful optimization has been performed. And now we can view a few things. Here is a summary table of your optimization. This column that you see here, objective from exact analysis, this is the actual weight of the 3-bar truss at the very beginning and at the very end. So here we started off with the mass of 4.82 and we ended off at a mass of 2.69. Here we have a history of the design variables. We started off with cross-sectional areas of 2, 1, and 1, and we ended off at 0.3, 0.8, and 0.8. Now, how do you view these results in Excel? Let's go ahead and in the same directory, we have a new comma separated value or CSV file created for me. This includes the same information regarding the objective and the design variables. And the great thing about this is now I can plot these in Excel. So for this, let me go ahead and take an existing template I have and show you what the plots will look like. Here on the right is an existing Excel template that I have. What I can do with this template is simply copy over the data from the left and copy it to the data or the Excel on the right. So let me go ahead and do that now. And then we'll go ahead and copy these design variables here. And then I'll move this to the very end. And then here, this is the initial design followed by design cycle 1, 2, 3, 4, 5, and 6. And then the last one's design cycle 7. So let's go ahead and take a look at what our graphs look like. And the reason I'm showing you this is because now you can see how to take your optimization data and view it in Excel. This might be a little friendlier than other methods, so that's why I want to show you this process. So here we have a plot of the weight during the optimization process, and this graph will show you a plot of the design variables through the optimization process. So here again we started off with areas of 2 and 1, and we ended off at areas of 0.3 and 0.8. So that's how you view the results in Excel. Let's go ahead and view the new structural results in, say, Patran. So these results I showed you at the beginning were the baseline results. This is before we perform optimization. During the optimization process, a new result file was created that contains the results for the initial and the new optimized version of your model. So here I'm going to point to that new version, and here bear with me while I track that folder, and we'll go ahead and pull in that result file and look at it here in Patran. So here I'll view the results or the displacements first, and here we have 0.02 like at the beginning. But what is the new result? Here are my result cases. You'll notice at the very end there are markers. There is a marker that says D0, another marker that says D7, D0, and D7. D0 is the marker for the initial model. So these are the results for the initial design. D7 stands for Design Cycle 7. Design Cycle 7 is where the optimizer found the optimum. So these are the new results for the optimized model. If I click on D7 and view the new displacement, my new displacement is 0.03 for both subcase 1 and subcase 2. But what about the stress constraints or the stresses in the members? Let's view those now. I'll select tensor. I'll view subcase 1. And then I want to view the X component, which is the axial stress component. So here, let's look at what's going on here. My negative 7,000 PSI is well above the negative 15,000 PSI for compression, so that member is good. This is 13,000 PSI, so in tension, so this is under the upper limit of 20,000 PSI. This member has an axial stress and tension of 20,000 PSI. So this element is right on the edge of the design constraint. So it's as if this member is limiting how much weight can be reduced in the structure. This is subcase 1, now subcase 2. We'll select subcase 2 and refresh the results. And since the loading was symmetric, we have the results almost the same, but in opposite members. So now this member is in 20,000 PSI in tension, and this member is in negative 7,000 PSI in compression. So that's how you validate the results of your optimized model. You always want to do this and make sure you're still having constraints that are being satisfied. Now, the last thing I want to show you in this demonstration is how to optimize your original model with optimized properties. So for this, let me create a new directory and I'll call it 3 optimized version. So you've already built your model in Patran. You've converted the BDF file to solution 200. The original model that you built has old parameters for the areas. These are specified in the PROD entry types. We still have 1, 2, and 2 here for the areas. How do you update this so it has the new area values? And I'll show you how to do that now. First, copy this original BDF file and paste it in your folder. This is the file we're going to update. So let's go ahead and open that and we'll move it to the right. So here's the file we're going to update. On the left, I'm going to update or open a new file. In the same folder where your optimization was performed, or PCH file was created. Open this file also. This file has the updated properties with the new areas. Here, my new areas of 0.83, 0.33, and 0.83 are here. And what I can do is copy this and paste it here and save it. And here you can see my new properties. And now this file on my desktop has the same model, but with updated parameters for the cross-sectional areas. And that was the last thing I wanted to leave you off with for this demonstration, a full beginning to end on how to perform optimization with Nastran. Let's go ahead and go back to the PowerPoint and discuss our next tutorial. This one's a very complex example. This one is having to do with buckling. Again, you can optimize for statics and buckling with Nastran Solution 200, so I thought this was a good example to cover next. This, I suspect, will take the remainder of the hour, possibly an additional 10 minutes. So just in case you have to go to your next meeting, there will be a recording of this presentation available right after this hour. So definitely come back to the YouTube channel and you'll find a link there. So now let's go into more detail regarding this example. Here I have a thin-walled cylinder with ring stiffeners that you see here in green. This is a cut section of half the model. The bottom edge is pinned and the top edge has an axial load of 10,000 pounds. There's a thickness associated with the shell elements, and there are beam cross-section dimensions for the one-dimensional elements for the ring stiffeners. So this is what we're going to do in this next tutorial. We are going to take this current layout of the model and we're going to vary some of the dimensions of the model. We're going to vary the thickness and I believe one of the dimensions of the ring stiffener. Our goal is to minimize the weight as much as possible while at the same time making sure that the buckling, or rather we avoid buckling in the model. I think this example goes into more detail regarding what our optimization problem statement is. We are going to vary one parameter, the thickness of the yellow shell elements. We're also going to vary dimension 2, which is the thickness of the ring stiffener. So that would be this gray section here. We're going to vary that during the optimization process. One thing to keep in mind is the offset of the ring stiffener. We want to make sure we avoid a situation where the cross-section of the ring stiffener begins to interfere with the thickness of the shell element that you see here. Let me zoom in just so you have a better understanding of what that looks like. So what we have to do is also impose an offset relationship that you see defined in this expression. We are going to define the offset as starting from this midline of the shell element, going up half the thickness, so that would be from this midline to half the thickness, so that would be here. And then we're going to go up half the height of the ring stiffener up to here. And that's given by this expression, negative 0.5 minus the thickness of the shell divided by 2. And since the offset is defined as positive in this direction, our expression should have a negative value in the end, so hence we have negative signs in front of both of these terms. So again, in addition to the design variables, we have to account for the offset to avoid interference of the thickness and the cross-section of the ring stiffener. And we're going to use this offset that you see on the screen. In terms of our constraints, our objective is to minimize the weight and our constraints. If we look back and look over the bending stress of a very simple example, we might have a stress distribution like the one you see here on the top right. So here we see that at these 4 corners we can have different bending stresses. What I want to do is, instead of constraining each point, I'm going to say take the maximum out of the 4 points and constrain that value. Here the maximum is 4.9. If I say take the maximum and constrain it so it's no more than 3 megapascals, this would just constrain the maximum stress here. So that's what I mean here when I say the max stress at end A for P bar L. So I'm saying take the maximum bending stress at point A or end A, constrain it, and do the same for end B. So take the other side of the element and constrain the maximum bending stress also. For the shell elements, we have a different stress constraint. We want to constrain the von Mises stress for the Z1 and the Z2 fiber of this example. So the Z1 would be one side of the shell elements, one fiber, and Z2 would be the opposing fiber on the other side. And of course, we want to constrain for buckling. So what we're going to say is constrain the buckling factor so it's no less than 1. A buckling factor less than 1 means that you are experiencing buckling. Anything more means you are avoiding buckling. So now let's go over what we're going to cover. 1, we're going to use the Solution 200 web app to create our design variables, our objective, and our constraints. We're going to convert our BDF file from Solution 105, which is a buckling analysis type, and convert it to Solution 200. We're going to perform the optimization, and then we're going to go ahead and review the results in Patron. So for this, again, we're going to use the Solution 200 web app. If you have any questions on how to get access, you can email me here, christian@theengineeringlab.com, and I'll definitely help you get access to this web app. Again, this is our goal. We want to minimize the weight, so we're going to reduce it from 5.76 pounds to 1.77 pounds. We want to make sure that our buckling load factor is greater than 1, and we're going to vary some of the structural dimensions of this model. So now let's go through the process. I won't open Patron just yet because you've already seen me show that in the last demo. What I want to do is start with the BDF file that you may have created. This BDF file is something you may have already created in Patron or your own pre-post processor. It's got information regarding all the elements, the properties, the materials, the loading, and all of that good stuff. I now have to convert this to Solution 200. Let's go ahead and go back to my web app and show you what the process is like. So let me close some of these folders just so we keep this clean. Here's my web app, and then I'll go ahead and click refresh so we start a new instance of the web app. Like before, let's go ahead and select all of these BDF text and paste it here in the web app. We'll go ahead and ask the web app to identify all the parameters that can be set as design variables. Here, I want to set the thickness and dimension 2 as design variables. And here, let me grab my nose just to make sure I'm selecting the correct items. Right, so the thickness and dimension 2 are set as design variables x1 and x2. I'll go ahead and specify bounds for these variables and say they're not to vary between 0.001 and 10. And I'll do the same for the upper and lower bound of the other design variable. So that takes care of our design variables, but we have to create the offset relationship I mentioned a moment ago. Again, we want to avoid the situation where we have an interference of the beam cross-section with the thickness of the shell elements. So for that, let's go ahead and open the PowerPoint and look at what our relationship was. So that is given here, and my relationship is negative 0.5 minus x1 divided by 2.0. So for this, we have to look for a new parameter that's called the W1 parameter. And now what I can do is set it as a dvxrel2. And now let's go ahead and do that. We'll go ahead and set this one as a dvxrel2. So I selected on this plus icon that moves that parameter to adjust dvxrel2. This is where I can type in that expression, negative 0.5 minus x1 divided by 2.0. Also, one thing I have to do is the maximum allowed values. This is important because during the optimization, if I don't impose limits on the offset, what could happen is if we say the offset is here, so I don't know, maybe I'll draw a center of gravity offset here. It's probably not the right thing to use, but it'll help in this case. Suppose this is the central or the midline here. I want to make sure that this never goes into this region of the offset. Because one, that's just not possible. It's as if the beam cross-section is literally going through the cylindrical wall. So what I need to do is impose an upper limit that says be no greater than negative 0.1. So we're essentially saying if you're in this region, that's okay. But if you're in this region, that's not okay. That's what the maximum upper limit means. So let's go ahead and impose that now. Type in -0.1 here. But now we have sort of a challenge. We have to do this for dozens of other offsets. You have to do this on an element by element basis. The web app has a wizard, if you will, to quickly do this for all of the parameters you see on the table. So what I'll do is I'll select this expression. I'll copy it and paste it here. And then for the upper bound, I'll type in -0.12. It's the same as before. When I click on this create icon here, I'll go ahead and set all of these offsets with the same upper bound and the same expression of -0.5 minus x1 divided by 2, which is good for me because now I can fly through setting all the offsets for dozens of ring stiffeners. And if we look here, there are honestly quite a number of elements we have to do this for. But again, the web app helps me address this. So let's go ahead and do this through page 2 through page 9. While I'm clicking here in the web app, kind reminder, if you have any questions, comments, you can leave me an email or you can leave me a message here on the right hand side of the screen. There's a chat box and I'll definitely address your question while I'm doing this demo or towards the end when I'm around for a few questions. Also, we are currently performing tutorial 2. If you want more tutorials on how to perform optimization, my YouTube channel has dozens of other tutorials you can follow, all with the web app. I think each YouTube video has a link to the PDF file, so you can definitely download and follow along. And as always, I'm here for any questions you might have. My goal with the presentation and with all this content is to really enable you with the capability to automatically optimize structures. So now here I've gone ahead and set the last few offsets with the given expression. And here, if I look, I have all of these offsets defined. And let me go ahead and inspect these and make sure these were configured properly and everything looks good. Let's go ahead and move on to the objective. Our objective is to minimize the weight, so we'll go ahead and select the weight here and minimize it. And now for our constraints. Here we want to set 2 constraints for statics. So we'll go ahead and select stress here and here. Let's go ahead and configure the stress constraint. We want to apply this to P-bar elements or properties. And we want to apply this to the maximum of end A and the maximum of end B. So that'll be item codes 7 and 14 that you see here. And now for the lower and upper bounds. So let me go ahead and type in 25,000 for both of these and positive 25,000. And now for the property IDs. These are the properties that are used to give the elements their beam cross sections. You could look inside of the PDF file or you can look inside a Patron to determine the IDs. Here I already have the IDs written out for me on my page. Alternatively, you can search your PDF file and find that you're dealing with P-bar L2. So here is the 2 representing the ID of the property. So we'll go ahead and type in property 2 here, 2 in here and here. And this finishes creating the design constraints for the ring stiffeners. I now have to do this for the thin wall of the cylinder. Let's go ahead and create 2 new stress constraints. And here I'll go ahead and type in P shell for this and that. And now I need to specify the element type I'm using for my shell elements. Here I know I'm using a C quad 144 element type for both of these. And now I can select an actual stress item code. Alternatively, what you can do is if you know the item code already, so for example, here I want to set the von Mises stress of Z1 as the item code. And here I know that item code 19 is the corresponding item code for the von Mises stress as Z2. So I can type in 19 there. Let's now type in P shell 1 here and here and the upper limit is volume AC stress, and we want to make sure it's no more than 25,000 psi. So just to quickly go over what we've done here. We've set the stress as a constraint type. We've narrowed the coverage of the stress. So here, these first two stresses are applied to elements associated with the P bar L2 elements or property. And here, the focus is limited to elements that are associated with the P shell 1 property type. There are a lot of stress types we can select, but we've only selected the end A maximum and end B maximum, and the same for volume AC Z1 and volume AC Z2. We then went ahead and applied our bounds. There's one other thing we have to do. We have to impose a buckling constraint. So we'll go ahead and select solution 105 and select buckling eigenvector value. And then here we want to set this buckling constraint to the first buckling mode, and we want to make sure that it's greater than 1.0. Now I've created all these constraints. It's time to create our constraint group. So what I'll do here is create and click on this constraint group. The first four constraints, R1 through R4, are for the statics subcase. So I need to remove R5 since it's a buckling constraint. This is applied to subcase 1. Now I'll create a second constraint group and type in R5. The R5 corresponds to the label here. So if I wanted to add another constraint, say R4, I could do that there. This second constraint, which again is the buckling constraint, is applied to subcase 2. As always, as you use the web app will automatically create the statements for you. Let's go to the exporter. We now see that the web app has converted my file from solution 105. It's converted to solution 200. It's included pointers to the constraint groups and the objective. Here on the right, I have statements for the design variables, the offsets, and then at the bottom, I have the objective and the design constraints. Now what I can do like before is download local versions of this to my desktop. So I'll go ahead and do that. Click download here and here. There are some augmentations I have to make to this PDF file. The reason is because this is a more advanced example of optimization. So once you're dealing with really difficult examples, some modification of the PDF file will be necessary. Fortunately, the web app will generate a majority of the statements for you, so you don't have to do this too much. I'll open the model PDF file and I'll explain what the edit is. This analysis statement has to be relocated, so I'll cut it so it's gone from there, and I'll relocate it under subcase 2. Here, the optimizer will see that for subcase 2, it should be optimized for buckling. And for subcase 1, I'll type in analysis equals statics. So what's going on here is the optimizer will optimize subcase 1 for statics along with its own constraint group, and then it will optimize subcase 2 for buckling along with its own constraint group. The first constraint group has all the stress constraints for the ring stiffeners and the shell elements. The second constraint group has a constraint for buckling. So this is the first edit. We also have to make a second edit. This is for the design model. At the very bottom is a line that is for the optimization parameters. So this sets settings for the optimizer. Here there is a capability called the truss region that's used by turning on T region and using a 1 here. Again, you want to make sure that you have enough spacing, so T region is in column 8 and the 1 is in column 9. So it's very important you have this appropriate spacing. Don't use tabs, use spaces when you're editing this. And so that's the last edit I wanted to make. Let me just quickly look at my notes and make sure I've configured this model properly. Everything looks okay. So we'll go ahead and perform the optimization. And now I'll take some time to go over what the truss region is. This is a very handy capability the optimizer has. If you want more details regarding what the truss region is, I refer you to the MSc Nastran Design Sensitivity and Optimization User's Guide. This is a resource I use very thoroughly over the last few months rather. In chapter 9, there are chapters on or sections on the truss region. So click here and you can read everything about the truss region. Basically, during the optimization, the optimizer will create approximate models of your model. So traditionally, when you perform an FE analysis, you'll form the stiffness matrix. You'll then have a vector for your displacement. You'll take the inverse and solve for your displacements, essentially. What the truss region does during the optimization, each design cycle has its own FE analysis, if you will. Sometimes those previously performed analyses can be recycled. This is in the form of an approximate model, where if the approximate model is still valid for future design cycles, it will reutilize the approximate model in the next design cycle. The benefit for us is that we can actually save time. So if something would take 40 design cycles before an optimized model is found, with the truss region, you could potentially minimize it to 30, 20. It's very case dependent. So in the model, I made the modification. I said, turn on truss region, set it to 1, meaning we're using the truss region. And it's going to recycle some of the approximate models during each design cycle. Again, I refer you to the Nastran Design Sensitivity and Optimizations User Guide that goes into more detail regarding the truss region. Alternatively, I will stick around after this presentation. You can ask me more questions, anything regarding Nastran Solution 200. And here we currently have the model running, and now it's finished. So now let's go ahead and look at the F06 file and see what we have. We want to make sure that we have the message run terminated due to hard convergence. So perfect. We have the message here indicating we've found an optimum. Let's look at the mass. We started off at a mass of 5.76 pounds, and we ended off at a lighter mass of 1.77 pounds. So perfect. We've been able to minimize the weight while varying the parameters of the thickness of the wall and the thickness of the beam cross-section. Here are the original values, and here on the bottom right are the new values. In my previous demo, I showed you how to view these results in Excel and how to optimize the original PDF file with the new parameters using the punch file. Again, the punch file has the new optimized parameters for the thickness. So here we have the new value of 0.013 and the new beam thickness of 0.0016. I think you've seen the previous tutorial, so you can replicate the same thing and optimize your original model. The one thing I want to do before we close is viewing the models in Patran. I highly recommend that after your optimization, look at your results in Patran, look at your model again in Patran. So here on what I'm showing you now is the original configuration of the original model. And then on the right, I'm going to show you the configuration for the new optimized model. The reason I'm doing this is to communicate the point that you should always inspect what your new result can be. When I was practicing this example, I found out that my beam cross-section, here, let me actually show you, had actually moved to the other side of the wall. And that's because I misconfigured the offset relationship in a previous example. So it's important, as I'm saying now, to always look at your results in your pre-post processor, verify the new dimensions, verify the offsets, and verify the new structural results just to make sure everything looks okay. So here on the right is what the new optimized model looks like. Let me zoom in very closely here, and you'll see that the offset is still flush with the thickness of the shell elements. And then I'll do the same thing here on the right. So here we'll zoom in very closely and we'll notice that we still have an offset from the shell elements just to make sure there's no interference between the ring stiffer and the wall thickness. And we can do other things like viewing the results. What's the buckling mode shape look like for this new result on the left and the right? What are the beam stresses? What is the von Mises stresses? Have I really satisfied all the design constraints? I leave this up to you to go about doing this on your own just to make sure you have the necessary procedure already established. And now I think I'll go ahead and pause it there and conclude this tutorial. Again, this tutorial, the goal of this whole webinar is to really communicate what the procedure is like for optimization. I know when I started doing optimization, it was initially a little complex, a little overwhelming. After months of experience using it, I can now communicate you what the best practices are. What are the best steps? What are the tools you should be using for this? What to watch out for? And as always, I'll be here to support you. My email address is here. Feel free to send me an email. I'm definitely here to support you. And just to summarize, we went over what size optimization is. There are a lot of optimization types out there. Here I wanted to start you off with size optimization. I went over when to use optimization. This could be when you want to minimize the weight of your structure. You could have a configuration for your model where it's not fulfilling all the design constraints. You can let the optimizer find a model that actually fulfills your design constraints. You might have a situation where your FE model doesn't match your experimental model. You can use optimization to bring the FE model to match your experiment. And also, if you're looking to study how an impact in changing a design variable could impact the performance, you can also do that with Nastran Solution 200. I went over the procedure for a very simple 3-bar truss example, and I went over the procedure for a really complex buckling example. Again, I wanted to start off small and really challenge you with something very advanced. As always, if you want more training, my YouTube channel has hours of training. Also, I'm doing these weekly training presentations. So if next week or tomorrow, actually, you want to see my next presentation on sensitivity analysis, you're more than welcome to attend that. In that presentation, I'll go over what a sensitivity is. It's surprisingly a very simple thing to understand. So again, feel free to come back to my YouTube channel for the latest schedule. Alternatively, you can send me an email and I'll definitely get back to you with the latest schedule. As always, if you want access to the Nastran Solution 200 web app, if you want guidance on a project of your own, let's suppose you're performing optimization and there's this odd message in your F06 file. Feel free to send me an email and I'll definitely do my best to help you. And with that, I want to give everyone a big thank you for being with me today. I'm open to thoughts, suggestions, ways to improve. If you have any questions, send me an email. Alternatively, I'll stick around for 3 minutes, 5 minutes. And you can ask me any question you might have regarding Nastran Solution 200. Thank you, everyone, and I'll see you on the next presentation.